Good evening, everyone. Did we lose Jerry?
I think so.
All right. At least I can hear some people, so I know I'm good.
Ready to wrap this up?
I don't know. The syllabus has weeks 9, 10, and 11 on the syllabus. Not sure what that means.
Yeah, BA has 2 more assignments after
Right.
this one that's due tonight. Yeah. Once I'm done, I just wanted to confirm one of the answers. Is he getting on? Or maybe he's a no-show?
Probably.
Hey, Mark, if you could go ahead and give this next TA session.
Wish I could. Wish I could. Thank you for the compliment.
Just we'll wait for another 5-10 minutes and log out.
He was here a minute ago. I mean, that's
Oh,
how
was
we
he?
all got in. But then he
Maybe
disappeared.
he's lost.
There we go. There
There
we
he
go.
is. He's back.
Oh, hi everyone. Sorry for the wait.
Jerry?
My computer
Hi.
cracked right the moment when I clicked start video.
What's the probability of that?
I don't know what happened. I'm not sure whether my video is showing, so I had to restart my computer. And well, anyway, let's catch up. How's your week 8 homework?
Good. Good. Yeah. I think
Mostly okay. We've got a couple of questions.
Oh, okay. All right. Glad to hear that it's mostly okay. Well, I don't see that my video is showing, so maybe there's something wrong with my camera. Okay. How about question 1? Where should we start today?
Uh,
Why don't you just go ahead and start at the top there, Jerry? Just, right at the beginning of question 1.
Oh, okay. All right. Well, let's see. There are 3 problems this time. Have you done most of them?
yes.
Okay, glad to hear. So all of them are regarding confidence intervals and p-values. I have created some short notes on this week's topic on confidence intervals and p-values. Let's see how they can be helpful. In problem 1, we have quality control issues. As we know, in product manufacturing, we usually do quality control by drawing a sample, then test whether the sample meets certain criteria. And in this case, we have average length of bolts considered to see whether the sample average length meets the criteria, so that we know whether the population we draw the sample from meets the criteria. And this criteria is that okay, we have 80 bolts drawn, and the average length of these 80 bolts were 6.2 centimeters, whereas the standard deviation is 0.1 centimeter. Now, first simple question. Do you think the statistics, that's the average length of 6.2 centimeter and standard deviation 0.1 centimeter, are sample statistics or population parameters?
I believe the 6.8. Well, it says the average, which is the mean, correct? And then he's given the standard deviation.
Mm-hmm. Yeah. My question is: are this average length and standard deviation sample statistics or population parameters?
I would say population, because you're dealing with the whole sample.
Incorrect.
Yeah.
Right, because it's dealing with the sample, they are sample statistics. The sample statistic, well, we don't have to concern whether we take the whole 80 bots as the sample or part of that as a sample. Any part of these 80 bots are sample. We draw these 80 bots from a large population, right? We don't just we don't just produce 80 bots. That's why all these statistics we are given in the question in the question body are sample statistics. Okay, now it helps us to answer first question. Which distribution would you use for confidence interval? Which have you chosen?
Normal distribution?
Yeah.
Distribution.
Okay, I heard two choices so far. Are there other options? Okay, so here the answer should be T distribution. The reason is simply that we have a sample statistics. And okay, now we need to calculate a 95% confidence interval. How did you calculate it?
It was given, we're using Thomas's statistical Excel spreadsheet that he gave us to utilize.
Okay, wonderful. At least you found the right file, but there are certain input cells we need to make correct. Let's see whether yours have similar or different input as I do. So here is the Excel sheet called statistics that's in the shared Google Drive. Well, you should be able to have used, you should have used it several times, unless you forgot where they are. It's in this Google Docs and Files link. Okay, in this file, we have several sheets. Now tell me, which of these have you used? Of course, this time, because we are calculating confidence intervals, we should use confidence intervals sheet. And here we have several blocks to choose from. There's one confidence interval for population mean, sigma known, and there's one confidence interval for population mean, sigma unknown. There's also one for confidence interval for population variance and another one for population proportion. So which of these four blocks have you used to answer part B?
Sounds like I
Here's
used
the
the
one
wrong
with
one.
the sigma is known.
Unfortunately, that'd be a wrong choice because here, what's shown as sigma, what sigma refers on the on this sheet is the population standard deviation. Remember that we always use Greek letters for population parameters, whereas we use italicized Latin letters to refer to sample statistics. And because in this example, we are given sample statistics about the 80 bots, that's why we use sigma unknown, because what's given here is not sigma, it's called sample standard deviation. It's not population standard deviation. Otherwise, the sigma is known as a population standard deviation. Any questions here? Okay, now we found the correct block that we need to use from this sheet. Now we need to explore what this block tells. Here, we need to find the input for sample mean, sample standard deviation, sample size, and confidence level. All these four are required to calculate both of these critical values and upper and lower limits of confidence intervals. So now let's find each of these statistics together. We already given the sample mean, right? I remember it was 6.2, and the standard deviation, that's sample standard deviation, that's 0.1. So we would put that here, 6.2 and 0.1. Remember here, we also have sample size to take care of, which is 80. That's the number of observations we have. And also we need to pay attention to what level of confidence we need to calculate. Here we also have 95%. That's a very commonly used threshold. So we keep that unchanged. We notice that we are given critical levels. These are about t-statistics, and we are also given the calculated lower and upper limits of confidence intervals. Here we notice that this confidence interval is around the sample mean, right? One of this, well, the lower limit is below 6.2, that's the sample mean. The upper limit is above the sample mean, which is 6.2. So in previous practice, some students made mistake about these input values. One of the methods you could use to check the correctness is that whether this interval is around the sample mean. If it's not around the sample mean, if this interval does not contain sample mean in the center, then that means we have made some mistakes in these inputs. However, I would encourage you to find out what happens if we put the same statistics into the sigma known situation with the knowledge that this approach would be wrong, but let's just see what happens if we do it. Let's copy and paste. We have exactly the same sample mean, but we just substitute this 0.1, which is the sample standard deviation actually, but use it as the population standard deviation. And we also have the same sample size here. Let's compare each of the results acquired from these two approaches. We find that compared to the correct approach, where we should recognize the sigma is unknown, if we somehow used a wrong approach, assuming the sigma is known as the sample standard deviation, we would find the critical value would be smaller in magnitude compared to the correct answer. We also find that the lower and upper limit would form a shorter confidence interval. So the lower limit would be higher, whereas the upper limit would be lower. So the length or the width of the confidence interval would be shorter than the correct answer. This is expected because if we go to the formula to calculate the confidence intervals, we notice that the confidence interval, if you click any of the limits, you notice the formula is nothing but a simple calculation based on 4 parts. We have the sample mean as the things we need to add or subtract from. We have B24, which is the critical value as the multiplier. We also have a B20, that's the sample standard deviation, as another multiplier. Wait. And we have the square root of sample size as the denominator. So all these 4 cells would come in play when calculating the lower and upper limits of confidence interval. We find that the lower and upper limits only differ by one of the multipliers, whereas the lower limit uses the negative value in critical value as one of the multipliers, the upper limit would use the positive value of the multiplier. So when we calculate, when we go into the formula, we notice that because the upper limits is calculated based on the critical value. So if the critical value is larger in magnitude, it will result in a wider confidence interval. That's why that in our wrong case where we have sigma known, when we have the critical values to be smaller in magnitude, we would have a shorter confidence intervals because the limits, because the critical values as one of the multiplier has a smaller magnitude. Let's do another simple practice. Here we want to see why we have different critical values. Just now we learned that because if we wrongly took the sigma as known, we would have smaller critical values. Let's see why this critical value would be smaller and how this critical value in Z and T are related or how they are different. This practice, I will simply change the sample size. Here, I would build upon what I have in the sigma known situation. Notice that it's a wrong approach. We should have used the sigma unknown approach. Anyway, I will change the sigma size and let's notice what happens to critical values. Sorry, I meant to build on the sigma unknown situation and see how that is different from the sigma known situation. So remember, what we are given is that the sample size is 18. What happens if we double the sample size? Let's see, 116. So before then, we recognize that our critical value used to be 1.99, right? And if the sample size is enlarged by 2, we find that both of these critical values, they are symmetrical. They are smaller in magnitude. And if we enlarge it even further, let's make it, okay, 1,600. So it's 20 times than what we were given. We find that it's very close to this critical value in the sigma known situation. Let's make it even more extreme. I will change the sigma, I will change the sample size to be, let's see, 1 million. Okay, here this value of critical values is numerically identical to the critical values of Z. This is expected. We know that since T follows a T distribution, Z follows a normal distribution. If the sample size of T, sample size of a T distribution is large enough, it means the degree of freedom is large enough. It approaches to a normal distribution. So that means if we are making any sample drawing, if the sample size is large enough, we could safely treat the sample distribution as normal without worrying about whether we know the sigma of the as the population standard deviation or not, because once the sample size is large enough, the the distribution, when we do not know the sample, when we do not know sigma, is almost the same as that we know the sigma, so it won't make a difference. All right, any questions here?
So Jerry, we can say that it's a normal distribution because it's over 30 for 1A?
No, we don't. So as we see that in my practice, if If I reverse the sample size as 80 as what we were given, we still find the critical value is somewhat different between these two, right? So we learned about the central limit theorem, and we note about a commonly used threshold of 30 to be a threshold of whether the sample size is large enough. But since in this case, we can calculate easily about the situation without sigma known, so we can easily acquire the results under sigma unknown, we should do it. The reason why historically we have a 30 as the threshold is that some of the distribution used to be difficult to calculate when people did not have easy access to computers. Now we do have easy access to computers, so we'd better calculate them if we can.
Thank you.
Okay, Percy, how did you address this? It's supposed to be an easy question since it gives you a hint that no calculation is necessary. If we enlarge the confidence level to be 99%, what happens?
The confidence intervals widen.
Great. Yes, you got it correct. How about other students? Did you have other thoughts? Okay.
Near margin will increase.
Yes, you're also right on that. That's also why the confidence interval would be wider.
Can you come again with that point? What is that point?
What I said is it's connected between the confidence interval width and the margin of error. We could easily see it through the formula of how confidence interval was calculated. As I showed earlier, confidence interval was calculated by a few inputs, right? First, we have the sample mean to build up on. And what's the rest is known as the margin of error, because this confidence interval was just subtract the margin of error or add the margin of error around the sample mean. That's why if the margin of error is larger in magnitude, then we would have a wider confidence interval. That's also why if we enlarge this 95% confidence interval to 99%, we notice that compared to now, the critical value was 1.99, right? If we increase the confidence level to 99%, we immediately find that the critical value is enlarged. It's 2.64 now. So that's why when we calculate the confidence intervals, the margin of error would be larger, and it will result in a wider confidence interval. Any questions here?
Thank you. Yeah, this is good.
Oh, okay. How did you answer the last part in question 1? What happens if the results had been based on a sample of 20? Oh, I think I happened to answer this question just now, right? Okay. Now you understand.
If there are more sample size, then it tightens the interval.
Yes, the interval would be shorter. As I illustrated earlier, if we enlarge the sample size, the situation would be closer and closer to the situation when we have sigma known. So if we enlarge the sample size to be a ridiculously large value, we would notice that the critical value of t would be numerically identical to that of critical values of z. But notice we will never have a critical value t to be smaller than critical value z. So the critical value z, that's 1.96, is the smallest we can ever get. And that's also why, because this 1.96 is close to 2, in many online resources, you would find a rule of thumb thresholds for critical values that will be taken as 2. If we calculate any t statistic or z statistic to be smaller than 2, we would recognize the hypothesis test we're doing is non-significant. If it's larger than 2, it's possible to be significant. All right. I believe we have some hypothesis testing involved in one of these questions, right? Or do we not have any? Did you have to calculate any p-values in this homework?
Not in this one.
No.
Oh,
No.
okay.
No.
All right.
I think
Then
it's
we can
next
save
week.
that to next
It's
week.
next week.
All right. In problem 2, we have a pool of around 1,000 people. Okay, 53% of them disapproved of President Biden. Oh, okay. Well, that's not too surprising. Well, we find a 95% confidence interval for the proportion. Then we find another 99% confidence interval for the proportion. What are the margin of errors and why are they different? Okay, now for this, how did you try to attack this question or 3 questions? Any tentative answers for part A?
Compute the confidence interval for population proportion using the statistics Excel sheet.
Okay, it seems you find the right block to calculate it. We have this one. That's the last one in the confidence interval sheet. Here in this example, we need to give the sample proportion, sample size, and the confidence level. Tell me which values should I input in these cells?
Sample proportion 0.53.
Oh, okay, great. Others, next.
1003.
Good. And the confidence level would be 95%. Notice
95.
here, what we need to put in here is the sample proportion. And somehow in this homework, we are conveniently given the sample proportion already. However, previously, there are other versions of the homeworks that says, for example, 530 of the residents disapproved of President Biden. In this case, what we put into sample proportion cannot be 1,530. So let's just see what happens if instead of a proportion, I put into some, count of residents that disapproved. Oh, we could not calculate the upper and lower limits, right? So notice here what we need to type as input is the proportion as a fraction instead of a count as a number of certain participants. Okay, but we also need to find whether we are calculating the right proportion. So here we need to calculate proportion of people who disapprove. If you were given a question about the proportion of people who approve, then you need to, calculate a simple different version of the proportion. So instead of 53%, we would type in 47% as the proportion of people approve certain things. Okay, any questions here?
Yeah, Jerry, I have a question.
Yeah.
So we keep referencing, and in my head I do the same thing. Like CNN poll says, 50%, plus or minus 3%.
Mm-hmm.
So yeah, I think the lower confidence interval and the higher confidence level interval is very straightforward.
Mm-hmm.
And then of course the margin of error. Are we supposed to give one number and then plus or minus, or is it? Because right now I'm giving both numbers, the lower and the upper, and then the margin of error. That's not very CNN-like.
Oh, okay. It depends on the news report style that you're
Okay.
required to do, right? So I'm not sure whether any of these two methods are better than the other, because the average audience may not be familiar with either of them. So if you ask anyone who read the newspaper, do you understand what margin of error is, without further reference, they may not give you a right answer. At the same time, if the audience is given a confidence interval, they may not interpret it correctly either. So but the reason we have both of these versions is that you understand they are totally equivalent. And to build on that, let's take a look at some of the notes I have. Let's first look at this proportion, okay? That's, well, I can call that as week 8 now. Confidence intervals. Okay, so about proportions, we know that these calculated confidence intervals was nothing but a slightly manipulation of what we calculate here as the confidence intervals for population mean. It's the same thing. We are simply transforming a binary category variable. Here would be whether a person approves or not, right? So we would code, because we are calculating proportion of disapprove, we would code that if a resident disapproves 1, otherwise 0, otherwise means the resident approves something, right? So we have this 1003, 0, and 1 observations. Then we calculate the confidence interval of the mean value. So let's simply do it here. We could, let's see whether it retrieves what we needed in this case. So here, the sample mean would be 0.53. We were not directly given a sample standard deviation, but we could calculate it. Notice here that in the formula for limits, for confidence intervals for the proportion, we find that here in the square root part, it's nothing but a but as a sample size, but as a product of B42 as the sample proportion and 1 minus B42 as the proportion of people who disapproved, right? Divided by this sample size. So here, hidden in the formula is how we calculate the standard deviation. So the standard deviation is simply the product of the proportion approving and the proportion of disapproving. So we do that here. We calculate this as 0.53 times 1 minus 0.53. And let me think whether I need to take a square root of it. Yes, I do need to take a square root of it. Ooh, okay. Because what I calculated just now was the variance. So if I square root of it, it'll be sample standard deviation. And we switch the sample size to be 1003. And we do the confidence level as 95%. So we see that they are slightly different because instead of a t-distribution, in our case, we use the critical value of z, right? That means if we copy and paste the whole thing to the sigma known situation, then we would retrieve everything required. but probably I would have to fix the sample size part because it has a, oh, okay. This formula was not changed. Now let's compare. They are exactly the same. Notice that the critical value is still 1.69 because this part is only related to the confidence level. It has nothing to do with the sample size or the standard deviation. It's the same thing as here. The critical value for population proportion. It's the same Z statistic calculated solely based on the confidence level. It has nothing to do with the sample size or any sample statistics. And we find the lower and upper limits of this case as what we calculated for population proportion is identical to those when we calculate population mean. That illustrates exactly as what I showed here. The population proportion is nothing but a manipulated version of the population mean. Notice that in this method, although it's simple and straightforward, it sometimes generates confidence intervals that's beyond the 0 and 1. For example, if we somehow got a sample proportion as, let's see, 99%, let's see what happens to the confidence intervals. Oh, okay, well, that's good, that it's still within 0 and 1. Well, let me fix it. Oh, okay, now you find that the upper limit of confidence level is beyond 1. This would be impossible because any proportion should be between 0 and 1. However, because of the convenience of this method, many people still use the simple method to calculate confidence intervals. But if you seek some better property of the confidence intervals, there are alternatives you can use. The one that prevents any confidence intervals to be beyond 0 and 1, the most popular and reliable one is Wilson confidence interval. I recall that it was created in 1927, so it was even beyond the first recession. So the old method still works pretty well. There are also other versions of the confidence intervals created for non-binary proportions. So for example, if we calculate proportions of education levels among your employees, the education levels could be high school or equivalent, some college, graduate school. If we have more than 2 levels in a categorical variable, we would have to calculate what's known as the multinomial confidence interval. Well, however, these Wilson confidence interval and the multinomial confidence intervals for categorical variables are beyond our scope of the course. So we won't discuss further on these. Just know that these are available. All right. Any questions about calculating proportions? All right, let's move on to the last part. That's okay. Last part is about income inequality. We have average household income, 58,000, and a standard deviation of 21,000. Okay, now we need to calculate certain probabilities. What is the probability that 50 randomly selected households have an average household income that exceeds 60,000? Okay. Well, first, we need to understand what we know. So could you tell me whether what we were given in the body of the question, 58 10,000 as average and 10 to 1,000 as standard deviation are sample statistics or population parameters.
Population parameters.
Oh, wonderful. This time you're correct. We are actually given as population parameters. Notice that here we are given directly that in the US, and these are not describing any specific sample. That's why these are known as population parameters. Any questions here? Okay, so how did you calculate the probabilities?
Use of normal distribution.
Yes, great question. Great answer. Could you tell me which sheet you used to calculate the proportion, the probabilities?
Yeah, probability distributions.
Great. All right. So here there are many versions we need to choose from. And which of these did you use?
Normal distribution.
Okay, wonderful. So here, notice that we are given the population standard deviation. That's why we are using a normal distribution. If we were instead given a sample distribution as, for example, saying sample standard deviation is something, then when we calculate probability, we would have to use a t-distribution. So in normal distribution, we need to put in 3 of the observations. So which values did you use as the inputs? What mean value did you use?
It'd be 58,000, right?
Okay, I'll take it just as you said. Okay, 58,000. How about standard deviation?
21,000 divided by square root of 50.
Okay. Did you have other?
Divided by square root.
Did you have other options?
Power of 0.5, yeah, whatever.
Power of 0.5. Oh, okay. Yeah, so to calculate square root, you could also use another version as like this, take a power of 1/2. You notice that it gives you exactly the same value. Okay, how about x? What did you use as x?
60,000.
60,000.
Okay. All right. So now we were given 3 or even 4 of them as the probability. Could you tell me which of these 4 values did you use as the answer?
So the answer.
Income exceeds 60,000. The 25.25.
Okay, so use this one. Okay,
Correct.
wonderful. Let's see whether this is correct. We would know that it depends on how this question is formed. We need to calculate whether this the probability is about the sample mean is greater than 60,000, right? So we immediately notice that what we are calculating is a cumulative probability. You could refer back to some of the notes we went through in probability 2 weeks ago about addressing probability questions. One of very important thing is to find the correct probability. We need to understand from the question whether what we are requested is a marginal, conditional, or joint probability. We're not playing any of these complex games in this case. However, we do have to take care of transforming the required value to be a to be a equation. So we notice that the equation would be exactly in this form. We are calculating the probability of a observed sample mean to be greater than some threshold. That's why we are using this value as the probability of a sample mean to be greater than 60,000. All right, with this, you should be easily able to answer question part B. So how did you answer part C? Why your results can be different?
So the selection increases, right? The size from 50 to 100.
Yeah.
So the higher the population, the more precise the response is going to be.
Let's see.
So your sample size is larger, and then your response will have a smaller
I see.
response, right? So 17% versus the 25%. You got a larger pool.
Well, I got what you mean, but at the same time, I detect that you might have confused with what precision means here. So precision is represented by margin of error, and it's directly related to standard deviation. And the standard deviation, although we know the population standard deviation is 21,000, right? But here, what we need to put into the standard deviation for a normal distribution is about the means, the standard deviation of mean. It's very different than standard deviation of observed income. Because of this, when we calculate the standard deviation here, that's why we need to take care of the sample size as we take a square root of 50 and divide the population standard deviation of household income. It's not the average household income. So that's why we have it here. That's different than the population standard deviation of household income. And when we have a larger sample size, this standard deviation in this normal distribution calculation would be smaller. And that means the margin of error would be also smaller. And in terms of the precision, you're right, it's more precise, but I won't say that did you say the observation was more precise? No, it won't make observations to be more precise. What's being more precise here is the measure of the sample mean, because the standard deviation, is built around the sample mean.
Thank you for the clarification. That helps.
Okay, yeah. So here, what's very important is understand whether we are measuring the mean or individual observations. So here, we answer the question about average income to be to exceed 60,000, right? We are not saying that how many of these 50 would have a larger household income greater than 60,000. Instead, the question is regarding the mean of the sample. And at the same time, what's given here is the mean of household income, but the standard deviation is not about the mean value. It's about the individually observed household income. That's why in calculating the standard deviation of mean, we would need to divide the square root of the sample size. Any questions here? Okay, now
Could you
let's
go over that? I'm sorry, could you This is Mark. Jerry, could you go over that? Why it's more precise? You said it's the measure of the sample mean. Is that correct?
This 58,000 as what we were given in the, yeah, sure. I mean, the 58, well, oh, no. Let's see. Okay, I mean, the 60,000, yeah, given here as an input is a sample mean, right? And enlarging the sample size would make the measure of sample mean to be more precise. However, I think what's more important is understand the difference between whether the question is about sample mean or individual observations. So let's make another section. Let's see, mean versus individual observations. So if question gives us mean, then, well, let's see. If question is about mean, we would need to transform sample standard deviation of individual observations to sample standard deviation of mean. These two are quite different. That's a very important part. That's exactly why in problem 3, we would have to calculate the standard deviation here, not just as given as 21,000, but we have to divide 21,000 by square root of 50, as shown here. The reason is here we are transforming the standard deviation of individual observations to standard deviation of mean. These two are different. All right, let's review some very important concepts of confidence.
So in this case, the z-scores will also get bigger, right? If you increase.
Excuse me, z-score.
Mhm.
We are not calculating any z-scores in part C. I mean, problem 3.
So
No,
we don't need to refer z-scores.
No, well, if you use this block, we won't have any z-scores calculated.
Okay.
Yeah.
Thank you.
All right. Well, confidence intervals. Now we have calculated several confidence intervals. What do they mean? For example, let's see. Earlier we calculated a confidence interval about well, man, they're all gone. Okay, how about I reserve it back to be let's take the example of proportions. In problem 2, we have calculated this confidence interval. How do you interpret it? Any tentative answers? Well, should I try call out one of you? How about Sadia?
Hi,
Would you like
Jerry.
to try?
I'm so sorry. I have like a migraine as we're doing this. I'm just trying to listen in. But I'm actually not feeling well. Thank you
Oh,
for trying
okay.
to include me though.
All right. How about another student? How would you interpret the confidence interval we just calculated in problem 2?
Well, I'll give it a try.
Okay.
That the confidence range of 49% to 56%, we have Let me see what I wrote here. I think that's the thing. Sometimes I get it, but it's hard to explain it.
Are we required to interpret any confidence intervals in this homework? I do not see it directly, but maybe you have already done the work.
I think it's in 1B.
Yeah, we have.
Oh, we do.
Yeah, 95% confidence interval for
okay.
average length
You're
of
right.
bolt and
Okay.
interpret it.
All right. Well, let's still use problem 2 as an example. So how did you interpret it? Would you like to try again? If you already open your answers.
So that would be 2B.
Mm-hmm.
So
Yeah.
2B,
So,
I have 95% confidence between 49.91% and 56.09% of population disapprove of President Biden. That's what I wrote.
okay. That's a very smart answer. You avoided many intricate and also easily to mistake part. So a very good option. I like it. So, well, maybe I would have to unmute one of you. Right. Okay. What I meant is that some of the online resources could illustrate incorrect interpretation. Before that, before understanding how to give a correct interpretation of the confidence interval, let's review what confidence intervals actually mean. When we have a 95% confidence interval, let's go back to my notes right in the first part. A 95% confidence interval. Here, the 95% means that if we sample the population 100 times, notice that each time we would have a different sample. A different sample could have a different sample mean, a different standard deviation, a different standard error, and a different sample size. And they consist of different individuals. So that throughout these 100 times of sampling, we could form 100 different spreadsheets consisting of different individuals selected in each of the sample. Then we construct or calculate a 95% confidence interval for each of the sample. Notice that we have 100 samples already. Then this 95% means that 95 of these 100 intervals we calculated are expected to contain a true population mean, whereas 5 are not. So because of this, we notice that this 95% describes a long-run performance of the methodology or the formula we use to calculate confidence intervals. But what it doesn't describe is the property of any specific intervals. So for example, it means we could not say that this confidence interval we calculated for the proportion between 50 and 60, between 50 and 56%, that 95% of the chance that it contains the true population mean or true population proportion, and 5% of chance that this specific confidence intervals does not contain the population proportion. No, we cannot say that. Instead, a correct interpretation would be one of these. Let me reorganize them. Ooh, okay. The interpretations we could make is that simply 95% confidence interval of house income lies between this, or in our case, it would be the proportion of disapproval would be between 50 to 56%. Or we could also say that any proportions in the range of 60 any proportion in the range of 50 to 56% is compatible with the data. Or we could also say that, this is about slopes. So we could save this example in the future when we calculate confidence intervals of regression slopes. But notice that here, none of these correct interpretation assign any probability interpretation to any specific calculated interval between A and B. So we would avoid these saying to assign any probability about the interval. Did you get it? Any questions regarding how we interpret confidence intervals?
Can you repeat it one more time?
Okay. So when we interpret confidence intervals, this 95% or 99% is regarding the long run performance of the methodology. It only comes in play if we draw many different samples. But in reality, what we were usually given is one sample that we do not have the luxury to sample a population many times. It's very costly. That's why when we interpret it, we should not give any probability related interpretation. Several of the correct interpretation I already gave here would be simply interpreted as we know that now that 95% confidence interval of something is between A and B, or we could say any population parameter in the range of A and B is compatible with the data. All right, we are approaching the end of our discussion. Any last minute questions? Okay, before ending, I would like to make an announcement of the midterm feedback form. This is anonymous. Once you click it, you should be directed to the Triple E evaluation portal. So I encourage you to take a feedback form for our review session. So once I collect, once the results will be made available, I would understand more about how I can make the review session to be better, or understand what area I can also get improvements. And glad speaking with you, and I hope you have a wonderful night while completing homework 8.
Awesome. And we'll see you Friday, Jerry, right?
Really appreciate it.
Jerry.
Oh yeah, I recall that Stephen forwarded me an invitation about a happy hour. Thank you.
Yep. Looking forward to seeing you. And you're awesome. Yeah. And I'm happy to fill out the evaluation as well.
Thank you. I have the evaluation
you.
form link at the top of the notes. I think I should also make a class announcement, so other
Yeah,
students
please do
could
that,
also
Jerry.
join.
Thank you.
All right. Glad having all of you this time. Good night.
Awesome. See you next week.
Thank you, Jerry.
Thank you,
We
Jerry.
love
Thank
you,
very
Jerry.
much.
Thank you so much for everything.
Bye-bye.
Thank you.
Bye-bye.